Hi everyone, in this video we will be covering the first section of the course. Chapter 1 deals with function and section 1.1 is a review of functions. We'll begin by defining what a function is. And that is a rule that assigns to each value x in a set D a unique value denoted f of x. That's the way that we read that, f of x. The set D we call the domain, and the range is the set of the values f of x. As x changes, as x varies over the domain. We use terms like independent variable, dependent variable, and then the argument. That's the expression on which the function works. Independent and dependent, those are defined also. Your text may define this, may write out this definition a little bit differently, but ultimately we are describing the same thing, right? The different words, but the definition is ultimately the same. We have a few different ways of representing functions, and the first can be just with a couple of boxes or a couple of circles, right? The first one we typically write domain, and the second one being the range. And I'll just throw some inputs, 1, 2, 3, and 4, and then my range 5, 6, and 7. All right, my function f maps from the domain to the range. Let's say I map 1 to 7. Let's say I map 2 to 5. Let's say I map 3 to 6. And let's say I map 4 also to 7. So that is a function the way that I have written it. Every element in the domain corresponds to a value in the range. No element of the domain maps to multiple entries in the range. So if I had 4 mapping to both 6 and 7, then what I've got would not be a function. So I can have things in the range come from different elements of the domain, still be a function. Okay, that's one way to look at a function. We can also define, or we can also describe functions just with our typical xy axes and then a set of points. This is my x-axis, that's the independent variable. This is my y-axis, that's the dependent variable. Y depends on x, and so let's say I have the point 2, 2. I'm just going to put 3 points on here, the point 1, 3, and the point 3, 1. Okay, so those are the 3 points in my function, okay? And so my x-axis is the domain. This element in the domain here, if x is 2, then its value is 2. If x is 3, its value, it corresponds to a y coordinate of 1. If x is 1, it corresponds to a y value of 4. I think I might have said 3 earlier. And the way that we can write this formally is that f of 2 is equal to 2. F of, I should have put 1 first, but that's okay. F of 1 is equal to 4. So when x is 1, the y value is 4. And then f of, that is 4, is equal to 1. F of 4 is equal to 1. There we go. So that's just a different way to write down, to represent a function. We can also represent functions as formulas. So by that I mean I can give you the function f of x is equal to, let's say, 3x squared plus 2. That, if we were to graph that, that would look like a parabola. But that's so this is a function as a formula or as an equation, and I can evaluate that at specific points. So if I have an input of 1, I substitute 1 everywhere I have an x, and then we find what the y coordinate is. 3 times 1 plus 2 is 5. So on that graph, we would see the point 1, 5. If this is familiar to you, enjoy it, right? While it's familiar and hopefully even easy, maybe, enjoy those moments, because in this course, that won't always be the case. You will see. We'll get to the more complicated stuff, but for now, this hopefully is review. Some of it hopefully welcome review, things you might have missed in some course in the past, or you might need a little brush up on. We can evaluate this at a negative number. Let's say we substitute in negative 2. 3 times negative 2 squared, add 2. I square negative 2, I get a positive 4. 3 times 4 is 12 plus 2 is 14. And so on that graph, we would have the point -2, 14. When we're looking at graphs, to quickly tell if a graph is or is not a function, we have what's called the vertical line test, and it says if a graph represents a graph represents a function if and only if it passes the vertical line test. Every vertical line intersects the graph at most once. Okay, so what do I mean by that? Let's say I have a curve that looks like this. This is a trig function that I've just quickly sketched, maybe poorly sketched. But if I draw a vertical line through that graph, let's make it stand out and be green. Everywhere that I draw a vertical line through that graph, right, it hits it once, exactly once. Okay, so that means that graph is a function. Okay, and really, to go back to the definition, every input, so this input right here, that x value, whatever it is, corresponds to one and only one output. This input over here, that x value, corresponds to one and only one output. This input way back here corresponds to one and only one output. What it would look like if we fail the vertical line test, let's say that I have a graph that is, let's see, I did blue before, so let's do blue. It's an ellipse. So an ellipse looks like a circle that got squished a little bit. That's a roughly drawn ellipse. This clearly fails the vertical line test. If I draw a vertical line in a few different places through it, it intersects the ellipse twice. So, and then to go back to the definition, this input corresponds to two different outputs. This input here corresponds to two different outputs, fails the vertical line test, not a function. All right, sometimes we're told to find the domain or the range of a function, and typically we start with answering the domain question first. So let's say I have a function f of x is equal to 3x plus 2. Okay, to answer the domain, what you really want to ask is, what x's can I substitute into that? Or really the better question is, what x's can't I substitute into that? Is there any number that you know of that you're not allowed for some reason, some mathy reason, to plug in for x? So could I plug in a negative number, a positive number, 0, weird decimal numbers? And the answer is there's nothing really that wouldn't work there. So for this one, we say the domain, because there's nothing that doesn't work, that means everything works. So we say that the domain is all real numbers. And you can abbreviate that by making a fancy looking R that looks like that. That's my fancy looking R. It's shorthand for all real numbers. Similarly, and if you think about what this graph is, it's a line. It's a line that's like shifted up to, has a slope of 3, right? That line goes up forever. That line goes down forever. So the range, that is also all real numbers. All the y values would be included on that line. All real numbers. All right. What if I have some other graph? Like let's say that my function f of x is equal to just a simple parabola, x squared. Okay. Is there anything that I can't substitute into that? The answer is no. So the domain is all real numbers. So my fancy looking R. All right, the range. Now this graph does not go up and down forever. This graph of this parabola, it goes up forever, but it doesn't pass 0. So a couple of different ways that I can write the range. I could write y is greater than or equal to 0. I could write it in a more formal set builder notation, it's called. I could write that the range is, another way to write it, the set of all points y such that y is greater than or equal to 0. And then with the fancy squiggly brackets, they're called braces. Excuse me. Okay, so a couple different ways to write that. Let's see. Let's say I have a fraction in my equation. Let's say it's f of x is equal to 3 over x minus 2. Okay, so what is my domain here? Are there any numbers that I can't plug into that? Well, there are. Domain. If I know one thing about fractions, it's that zeros are bad in the denominator. We don't like dividing by 0. It doesn't make sense. 3 cookies divided by no people doesn't have a good answer. It's undefined. It's not defined. So the domain is the set of all points x, such that x cannot equal 2. All right, so how did I know that? I took my denominator, x minus 2, and I set it equal to 0. Not 2. I set it equal to 0, solved for x equals 2. But really, we're saying x can't equal 2. That's bad. That doesn't work in this function. I'm going to skip answering the range on this one. I'm less likely to ask you for it, but in the text, in the OpenStax text, it does go into how you find the range for this one. All right, and last, let's do one more involving a square root. And let's see, what is my function for my square root? I lost my place. There it is. All right, my square root is, let's say it's f of x is equal to the square root of x minus 5. That's my function. All right, and so for the domain of this one, right, we got to say what doesn't work with square roots. Well, I can take the square root of 16, but I can't take the square root of negative 16. Well, I can, but we get into imaginary numbers, and we're not going to really talk about them this year. We don't get into them in calculus. All right, so when will I have a negative number, right? Well, I'm going to take that expression under the radical sign, x minus 5, and in this one I'm not going to set it equal to 0. I'm going to set it greater than 0. I need x minus 5 to be positive. Actually, it can be 0. I can take the square root of 0. So really we're going to say greater than or equal to. If I solve that for x, we get that x is greater than or equal to positive 5. All right, so x is greater than or equal to positive 5. So for my domain of this one, it is the set of all points x such that x is greater than or equal to 5. Okay, just like the last one, I'm not going to do the range of this one. Maybe we'll talk about that in a different video, but for now, we'll just end with domain on there. Okay, another way to write each of these domains is using interval notation. You've hopefully seen that before. Interval notation looks like this: 5, comma, infinity. I used a bracket, a square bracket on 5, and a parentheses on infinity. It includes the 5, does not include infinity because infinity is not an actual number. Let me add the interval notation up here. Whoa, that was bad. Square bracket and 0, comma, infinity. For this one, for a not equal to, we need to use 2 sets of intervals. It's negative infinity, comma, 2, and then a union 2, comma, infinity. Okay, if you want more detail on interval notation, let me know. I'll either find a YouTube video or record something additional if you're not familiar with that. I'll probably go back and forth, but I may end up using interval notation most frequently. Next, we'll talk a little bit about composite functions. Sometimes they're called nested functions. We write compositions using this little circle, f composed with g of x. We can write it again with the circle, or we write them with the nested parentheses f of g of x, and you evaluate them really in 2 steps. Okay, and so a quick example, if I have f of x is equal to x squared, and g of x is equal to x plus 5, I can find the composition f of g of, let's say, 3. Or I can find the composition g of f of 3. All right, and to do those, first we find g of 3, right? We work on from inside out, basically. G of 3, I'm going to take, so I'll leave my outer parentheses. Probably should have given myself some more space there. There we go. F of 3 plus 5 is f of 8. So then we plug 8 into the f function. So then we get 8 squared, which is 64. Right? If you change the order, does the answer change? Let's find out. F of 3 is first, so we're going to find g of 3 squared, plugging 3 into the f function. Or that's just g of 9. which is equal to 9 plus 5, because that's what the g function says to do, which is 14. 14. Okay? So that's one little example of composite functions. Again, your text has a few more examples. Sometimes we like to use graphs to talk about composite functions. So I have the black graph is y equals f of x. The red graph is y equals g of x. And so let's say I have to compose f of g of, let's say, 7. Okay? So f of g of 7. Work inside out. G of 7 is first. Okay? So I'm going to go to 7 on the x-axis and see where my function is. Oh, it's right there at, let's see, that has a height of 2. So g of 7 is equal to 2. Well, we still have f left to do. What is f of 2? So now I'm going to go back to 2 on the x-axis and see where my f graph is. It's kind of an ugly point, but that's because I picked a number off the top of my head. But let's call that 4.5. F of 2 is 4.5. All right. We could also compose a function with itself. Okay, so by that I mean I can take f of 4. So we're composing f with itself. So if I start at 4, where is my f graph? Well, it's all the way up here at what looks like 8. So then we have to find f of 8. So we did the inner f of 4. Now we've got the outer f of 8. So I'm going to find 8 on the x-axis. Where is the f graph? Looks like it hits right there at 6. Okay, so we can use a graph to figure out these compositions too, and I always kind of like the fun back and forth, going from one graph to the next, and where does that 7 that I started with, where does that lead me at the end? Okay, and then you can read through these. If I have a graph that is symmetric over the y-axis, that means you can take and fold the graph on the y-axis, right? If x, y is on the graph, then the opposite of x comma y is also on the graph. So the y-coordinate is the same. The x-coordinate is positive and negative. Symmetry over the x-axis, I can fold it over the x-axis. It's the opposite property. And then if it's symmetric about the origin, whenever xy is on the graph, then negative xy is on the graph. And what that means is, well, actually a quick visual of each of these. Symmetry over the y-axis, the first one, right? If I have let's go with 3 different colors each time. If I have a point up here, its matching point would be there. That's the first one, symmetry over the y-axis. Over the x-axis, if I have a point, say, over here, its match would be over there. That's symmetric over the x-axis. And then, oops, I didn't label my x-axis. There we go. Symmetric with respect to the origin, or it says, sometimes we'll say about the origin. If I have a point that's green up here in the first quadrant, then negative x, negative y in the third quadrant would be down there. Or it would go from the second quadrant to the fourth quadrant. Okay, so that would be symmetric with respect to the origin. Finally, we'll close out the section with symmetry in functions. When I look at a function, how do I know if it's going to be symmetric or not? An even function, f of negative x is equal to f of x for all x in the domain, we say. And an odd function, f of negative x, notice that negative is out in front there, is equal to negative x, f of x for all x in the domain. Okay, so how do I use this property to help me know information about functions? Well, let's say I have f of x equals, let's go 5x to the 4th plus 7x squared minus 2. All right, so what I'm going to do is I'm going to plug in a negative x into that function and then see what happens. F of negative x, if I plug that in, a negative x in for the x there to the 4th power, 7, a negative x goes there, squared, minus 2. Okay, what happens? Well, when I take that negative x to the 4th power and that negative x squared, when the exponents are even, right, a negative number squared or to the 4th power or to the 6th power, that answer is positive. So I can rewrite this as 5x to the 4th plus 7x squared minus 2. It didn't change. What I started with is what I finished with, right? So what that means is that is an even function. All right, it's symmetric with respect to the with respect to the y axis. And then my odd function, so this one ends up being symmetric about the origin. I'll give you an example of one there. If I have, I'll do a shorter one. F of x is equal to x to the, oops, not to the second power, that wouldn't work. X to the third power plus x to the fifth power, let's say, right? If I plug my negative in there, negative x to the third power, negative x to the fifth power. Well, what happens when you cube a negative number, or when you put a negative number times itself 5 times over, right? That answer is negative in both cases. So this is negative x cubed plus negative x to the fifth. I'm basically pulling that negative out of the parentheses because that's what happens when the exponent is negative. All right, well, now I can take that and factor it out of both terms, x to the third plus x to the fifth. And so what I've got, I started with this, I ended with negative that, I ended with negative my function, right? That's what it means for it to be an odd function, and that would be symmetric about the origin. Okay, so I know I threw a whole lot at you. That would be like an entire chapter in another course that's not called calculus, but in calculus, it's day 1. It's a lot. Long story short, the more familiar you are with this preliminary content, or the better you refamiliarize yourself with it, the better off you will be progressing through this calculus course. So we didn't do any calculus yet, right? Day 1, this is all review, hopefully. If you're seeing it for the first time, maybe talk to me. But it's review of things that will help you to be more successful over the course of the next 15 weeks. Next step, go work on the homework for section 1.1. Thank you very much for listening. Have a wonderful day.